So let me just say quickly. So today we're happy to have Stefan talk about determinism, indeterminism inside black holes. Thank you so much, please.
Yeah, thanks. So I'm continuing the talk I was attempting to give 2 days ago. I'm sorry, no. Okay, so I can go over this. I think I can go over this. All right, Schwarzschild black hole. An observer A falling into the black hole. He ends her existence after a finite proper time inside at the singularity, which is space-like. So this is nothing particularly new. You can look at the same kind of situation in a Reissner Nordström space-time, which drawn here on the left, which is physically a charged black hole. It does look qualitatively different in the interior in that you have a kind of inner horizon there, and you have the possibility to actually cross that inner horizon and stay clear of the singularity. You know, it would seem so, at least from this Penrose diagram. The issue with this space-time, and as far as the interior of the black hole is concerned, is seen in this diagram, where I'm drawing the maximally extended version of this just to make this look more intuitive. So if you imagine you have access to all fields and their all initial data of any possible field on this initial surface sigma, then according to the laws of wave propagation, you are able to predict the fields inside this diamond-looking like shape here, which, the point is, this does not include this region beyond the so-called Cauchy horizon here. And so this is a breakdown of determinism even in classical theory. So there's no way to further extend this surface so as to include, so that the domain of dependence also includes these regions behind the inner horizon, or Cauchy horizon is the same thing. Okay, so is this a problem? I think it would be, but there is an old argument, which is a kind of a blue shift type argument, saying that signals or from emerging from the exterior of the space-time falling into the black hole, they're incredibly blue shifted at the Cauchy horizon, and therefore lead to a divergent stress component TVV. And such a divergent stress component would, via the Einstein equations, lead to a divergent metric, or a singularity at this right at the Cauchy horizon. So in fact, eliminating basically this region here. So that's what's called strong. I mean, that's called. I mean, the idea that this should happen is called strong cosmic censorship, not to be confused with the other form of cosmic censorship having to do with naked singularities. That's an entirely different thing. Just they're both called cosmic censorship. They're both referred to as censorship, but they really apply to entirely different situations.
Sorry, just a quick question. So
yeah.
This censorship says that the inner horizon has to be unstable, or what does it
it says that the inner horizon, in fact, is a singularity if you turn on perturbations.
But if it were not a singularity, then a time-like observer can reach the singularity to the future of I plus, right?
Correct. So, then he or she could cross it without burning to crisp, and then she wouldn't be able to predict what happens to him or her as beyond this Cauchy horizon.
But in their future, they could end up at that singularity, and that's like is that similar to some sort of naked singularity thing as well? Because
sort of, yeah. So the region beyond the Cauchy horizon has a naked singularity, and it's kind of unpredictable what's kind of happening there. So in a flash, you cross to a region where you have no idea what is going to happen. So this is very strange. So it's reassuring, or at least that's the idea, that this kind of thing doesn't happen because this region is non-existent really. I'm just mentioning this. Please note these null coordinates v going here across the Cauchy horizon and u going along the Cauchy horizon. And v is sort of defined so that it's 0 here on the right on the horizon. So divergent quantities will always be expressed as powers of this v then here, or inverse powers. Okay, well, that's the upshot. So I think I came to this. There's a similar story if you turn on a cosmological constant positive, in the presence of which you still have this region. The infinity looks a little different, but that's not so relevant to this problem. But there is a twist to this blue shift effect, because in this region, which represents the exterior of the black hole, the universe, so to speak, you have an exponential expansion, and that causes a redshift. And the redshift is opposite to the blue shift. And so these effects can compensate each other to the extent that at the Cauchy horizon, you do not have this kind of singularity. And in fact, these are just words, but this has been studied in a lot of detail now, starting with early work by Mellor and Moss, also by Brady, Moss, and Myers, more recently by Harvey Real, Jorge Santos, and Diaz, who have, in some sense, made important corrections or clarifications of this earlier work. Anyway, so the upshot is that the stress tensor in this scenario with a cosmological constant, it does not diverge as v to the -2, but it diverges only as v to the -2 plus something. And this something is a constant called beta, which expresses this competition between red and blue shift I was talking about, wherein alpha is the so-called spectral gap of quasi-normal mode frequencies, and kappa minus is the surface gravity of the Cauchy horizon. So the surface gravity expresses kind of the blue shift effect, meaning that beta is larger when this kappa is smaller, so having leading to a bigger blue shift. And the spectral gap expresses kind of the decay of waves in the exterior, so it expresses this a redshift effect. And so, without describing this in a lot more detail, explaining what quasi-normal modes are, etc., it is important to note that you can cook up values for m, q, and lambda, so that this beta is, for example, bigger than 1/2, and then this stress tensor diverges only as v to the -1. And if you translate this back to a metric, then it means that the metric is nice. So it's nice enough for you not to get burned to a crisp. And so that means that you can get even very close to 1 there. So that means that in the presence of a cosmological constant, you have this cosmic censorship solution to the original problem doesn't work. And so this numerics has been worked out by in a paper by Cardoso and others, and this more mathematical analysis is due to a bunch of people, really. I mentioned mostly these Hinz and Vargy, this contribution by Hinz and Vargy, which is the one that is kind of explained here. But I should also definitely mention work by Terfermos and Luke, as well as these other people here who have also looked at this problem, not so much always focusing on the case with the cosmological constant. Okay, so given...
Quick question.
Yeah.
So this range, whether you violate the strong cosmic censorship, does it correspond to large, let's say I fix a cosmological constant, does it correspond to large mass? Is it near
No,
extremal?
well, there are different regimes where this can happen, but for example, in the near extremal limit, it does appear to happen, for example.
So if you're very close to the extremal?
Yeah, so close. I mean, I figure I'm going to show some values later. Yeah, it also depends on the mass of the field. I mean, in the original analysis, this was set to 0, but if you think of a field like the Higgs, then it should obviously have a mass. Yeah, it depends on different things. It's kind of a bit hard to picture, and I'm not sure that they have really scanned the entire range of parameters. I should check, but I'm going to show some graphs later. Okay. So you have this problem classically. So this is all classical physics, classical waves propagating on these curved spacetimes. So now, given that you can't apparently solve this indeterminism problem with classical waves, at least in these cosmological black holes, you can ask whether quantum theory is going to do anything for you. If you could solve the problem with classical waves, then you wouldn't have to worry about quantum fields because, typically quantum corrections are small. But given that you can't do it with classical fields, it seems a relevant question. And in fact, some time ago already, Ori and various people looked at this kind of thing in the case of the Reissner Nordström black hole, and also Diaz and et al. Looked at the BTZ black hole in 3D, which is a black hole actually with a negative cosmological constant, but it has a kind of similar story. I'm going to come to how our work differs from that later. Okay, but so we take in the quantum field theory, what we want to do is kind of the same, in quote, as in the classical theory. So we want to set up an arbitrary state or a generic state initially. So I'm going to call that state psi. And then the state, i.e. its correlation functions, are determined up to this Cauchy horizon here. And I want to investigate how the stress tensor, the expected stress tensor, behaves, or its expectation value behaves as I cross this Cauchy horizon. So the expected stress tensor is the analog of this classical stress tensor there. And so also in the classical case, if you want to make a statement, if you want to make a statement here, you better assume something about the initial data, because let's say if you had an initial datum which corresponds to a shock emerging here, then there's little surprise you're going to find a corresponding shock at the Cauchy horizon. So that's not what you're interested in. You're interested in something that behaves perfectly smooth, and you ask whether the propagation of this perfectly smooth thing will result in something singular necessarily. So likewise, in the quantum field theory, you want to start with a quantum state that's not necessarily the vacuum, because it's just a very special state, but a kind of a generic, well-behaved state that does not correspond to having shocks or particle sources or things like that, someplace, intense particle sources. So technically, if you're just looking for a free field, which is kind of all I'm doing here, and that's going to be enough, that means that the two-point function should behave at short distances, just like the vacuum two-point function in quote. So technically speaking, what you want to demand, and that's kind of well established that this is kind of the right notion here of a regular state, is that it's a Hadamard state, which just means that its singular part is a certain geometric quantity over the signed geodesic distance squared, which would be x1 minus x2 all squared in flat space, and then a logarithmic term, and then a smooth term which is dependent on the state. So there is a kind of a universal geometric part which is independent of the state, and then all the state dependence is only in the smooth part. That's what it means, Hadamard. And so this is a kind of right thing to do. So in flat space, if you take the vacuum and you excite it with any kind of reasonable wave packet, then you get a Hadamard state. Or if you take a thermal state in flat space, or you excite that with a reasonable kind of wave packet, or with many wave packets, then it's always a Hadamard state. So it is not a Hadamard state if you excite it with a wave packet corresponding to a shock or a singular kind of source moving along, let's say here. So that's the kind of idea. Anyway, so this is a technical assumption, and what we proved in this.
Sorry, can I ask a quick question?
Yeah, sure.
So can you say a few words about the physics of the log terms? does this have to do with the mass, or?
Yeah, so in flat space, you'd have the log term as well if you have a mass. So if you just take the 2-point function in flat space, in position space, it will have the 1 over x1 minus x2 squared, and it will have a log as well.
So basically, it's just Hadamard type here means that the divergent piece of the correlator 2-point function is the same as flat space, whatever.
Well, it's not in, so in flat space, it would mean exactly what you say. So now we're in a curved space. So also the singular part has to be adapted by the geometry. But the point is that this delta and this V are certain geometrically defined quantities, like the geodesic distance. This is the so-called Van Vleck determinant, and this is some sort of related quantity from the theory of geodesics. So it's got to have this form for it to be a solution to the wave equation. I mean, if you assume this kind of singular term, then the form of this V and delta is just determined by some transport equations. This is quite old stuff. So.
Okay, so I do have another question. Maybe if it goes back to the previous slide, but so if you want to postpone it for later, that's fine. I wanted to ask, is it known what is the endpoint of the instability that you mentioned in the classical case, for example, for the inner horizon of a black hole?
Yeah, it's a weak null. Well, that depends on how strong is the. How strong? I mean, if it's really like V to the -2, like this, then I believe it's then it's it should be a null singularity with the metric blowing up logarithmically. If it's slightly better than this, it's a weak null singularity with the metric still being continuous.
I see. Thank
across C. And it turns out that in the asymptotically flat case, it turns out to be a weak null singularity with a continuous metric. Whereas if you have okay, so the proper way to think about it is whether you can. I mean, and Christodoulou pointed this out. I mean, the proper way to think about it is, is the metric regular enough to continue it as a weak solution across the Cauchy horizon, and in multiple ways. Then you have this indeterminism problem. And so if it's, for example, so he gave criteria, and then if this kind of singularity would would definitely not allow you to continue it as a weak solution.
Thank you.
Okay. Right. Okay. So our result is the following. So we compute the stress tensor, or the VV component, which is the one that should blow up. And as we compute its expectation value at the Cauchy horizon here or near it. So basically you'd have to take the state and propagate it up, and then compute the renormalized stress tensor up here. And this is of course a very difficult problem. So you can't write an explicit solution, given even that the state is supposed to be generic. But you can say something to answer this basic question, which is that it's got a leading singularity, which is of the form c times v to the -2, and this c is entirely due to quantum effects. So if it would have an h bar in front if you put h bar back. And it only, furthermore, depends on the black hole parameters, which are m, q, and lambda. So it does not depend on the state. So it's completely universal in this sense. Whereas the state dependence is expressed through this little tvv, and the little tvv, well, it depends on the state, but this depends like the classical solutions. So in the classical solutions, we said it behaved like this. And it turns out the state-dependent part behaves just like that. I mean, the proper statement is with some Sobolev spaces, etc. But I mean, it's kind of, you can think about it this way. And so this very divergent quantum piece here causes this divergence, which will shut off the space-time, which will replace the Cauchy horizon. Basically, that's at least what you think. Upon back reaction, if this were to be included, it would convert the Cauchy horizon into a singularity. So it is, however, important to note, and that this was also already pointed out by Ori, who and his group, and especially I should mention in this regard Noah Zilberman, who's written a couple of papers on this. So they did the calculation for a specific state, or a specific, very special state, and finding this in kind of these very special states in the asymptotically flat context. And they also pointed out that the sign of this C is important for several reasons. So if the C is greater than 0, then the average null energy condition holds near the Cauchy horizon, and this means a kind of a positive energy density, and a positive energy density always causes the test bodies to converge, and since this term, the overall term, is divergent, it's positively divergent in this case, so it will squeeze you to death, if you like. Whereas if C is negative, then the average null energy condition is clearly violated, and this corresponds to sort of anti-gravity, if you like. And in this case, you're stretched to death, so it's kind of like this. In the case that C is 0, you only have this classical piece, I mean, classical in quotes, because it behaves like a stress tensor of a classical solution. And then you'd be back with the indeterminism problem. So it's important that C is non-zero for this to help you. Now, I think I've just used this here. I'm just showing this again. So this is my slice, the Cauchy horizon, some object approaching it like a galaxy, and if the constant is greater than 0, the galaxy is squeezed, whereas if it's less than 0, it's kind of stretched.
Sorry, can I ask a question?
Yeah, sure.
how do you understand this, the fact that the H-bar perturbation theory fails? So you're saying that you're getting a quantum correction that is very, very large, much larger than the classical piece.
Yeah.
What is the physics of that? That's very atypical, right? What has
Sure.
caused that? And it's also, I mean, how reliable is the calculation that we were doing at that point? Because we're treating matter quantum and gravity as classical.
Yeah. Right. So it's a semi-classical calculation, as you're pointing out, of course. However, I mean, if you put the constants back, so there's an H bar here. The whole thing is supposed to be morally on the right side of Einstein's equation. So there's a G Newton as well. So it's G times H in front, which is kind of the Planck length. So the Planck length squared. So this effect is going to become important around a Planck time before you cross the Cauchy horizon. And as this, and when it's of order 1, of course, by that time you're going to at some point need quantum gravity, but it's going to be, enormous before, quantum gravity is supposed to take over. So of course it's the usual thing that the true nature of this singularity cannot be
I see.
described using this semi-classical theory. But until you hit it, until you reach these Planckian energies, which is, you reach quite huge energies. Then until then, it should be perfectly fine. But of course, once it is Planckian, then it's anybody's guess. But that you can say even about the Schwarzschild black hole singularity. It's the same problem there. Okay, but of course it's a semi-classical analysis. So now I'm pointing this out that the behavior C is important, whether it's positive, negative, or 0. So you got to calculate it. It's calculated by a quantum field in curved space calculation. This result is a mathematics result that can be split in this way, which cannot be found by any kind of explicit calculation, but you have to use some fairly advanced tools of mathematical analysis. But the calculation of this C, which doesn't depend on any state, is something that you can calculate, at least numerically. And so that's what we did, and what for very special states Ori and his group did. And I'm using here a plot. So I'm plotting Q over M, where Q over M equal to 1 is the extremal case. And then I'm plotting M to the 4C, which is a kind of dimensionless quantity. I have no idea why it's called a C tilde here. And you see it's kind of dips down clearly for at least some values of the cosmological constant. I forget now which values you have. So it's quite clear that near extremality you have a negative C. So you have this kind of stretching violation of the ANEC here, and you have a 0 somewhere, but this is obviously just going to happen for an extremely special value of Q and M. So it's a highly fine-tuned situation. So it doesn't matter really that you have 0 sometimes. It's irrelevant physically. And you can also do this by looking at how this varies with the mass of the field. Again, for certain values now of the black hole parameters, and you see that you tend to have a positive C when the mass is sufficiently big, according to this graph. And these different colors represent different choices of the black hole parameters, which I don't recall at the moment. but it's just supposed to give you some sort of a qualitative idea.
Sorry, just one quick question.
Sure.
In these type of space-time, so the cosmological constant is positive.
Yeah.
Do we expect anything like the average energy, ANEC, as a constraint, like some sort of lower bound on the integral of TVV along a null line, or not?
I don't think you really expect the ANEC in curved space in the first place. I think you expect it in some sort of back-reacted theory at best. So I don't think you're going to have the ANEC in a curved space-time generically. And I think you use
ADS.
No, I think ADS is different. So, if you take any curve that's along a bifurcate Killing horizon or a conformal bifurcate Killing horizon, you should be fine. But yeah. Which in Minkowski space means any null geodesic. But I think in ADS it's the same.
ANEC in ADS has been used in various discussions in holography, at least.
Yeah, no, I think these highly symmetric spacetimes may be different, and deSitter space possibly also. I think perhaps not. But a generic curved space, I think it's more like that back reaction may enforce this ANEC, but without back reaction, I think you just don't have it in general.
I see.
Though in very special space times you may have it, like Minkowski space, you have it, and possibly ADS. Couldn't tell you off the top of my head, but I'd say yes, I guess. But certainly not in this black hole space times.
So is the moral of these plots that for generic values in the parameter space, this C parameter is non-negative? It's not zero, sorry.
It's not zero, exactly.
Non-zero.
So that's exactly what so for non-generic values, so there's always a fine-tuned, see, it looks like there's a fine-tuned value also of the mass and so on, where it is zero, but generically it's non-zero. So generically you have this flash of enormous stress energy coming at you as you want to cross the Cauchy horizon during the last Planck unit of Planck time. Okay, it's like a firewall basically. I'm not at all. I'm using really conventional ideas about quantum field theory here, but you could use the terminology firewall for this phenomenon, except that it's a firewall at the inner horizon. There's no such thing. There is no. I should emphasize there is nothing whatsoever special going on at the event horizon. It's just perfectly normal. It's just at the inner horizon that this happens. Okay, I don't think I want to go through any ideas of proofs or whatever. I just want to mention that this constant C, the way it's calculated is by looking at a kind of double scattering problem where you scatter modes in the outside and look what's scattering in, and then you scatter that again of the angular momentum barrier, so to speak, and look at what's ending up at the Cauchy horizon. And you do this kind of problem, and then analysis tells you that the constant C is related to is an integral of a kind of energy momentum density, omega NL, where this NL is sort of the number density at the angular momentum. L is, that's a kind of expression in terms of these scattering coefficients, R1, R2, etc. And so once you know the scattering coefficients, C, at least you can compute the first couple of angular momentum values, and you find typically that this sum really goes down extremely fast. So for these values, at least of the parameters, computation of the first few, S wave, P wave, and maybe one more, but that's usually sufficient. And then you have to do this integral, and so you do this computation of the scattering coefficients for each value of omega. There is a substantial amount of technology for computing these scattering coefficients. That's closely related to solving the Tukhowsky equation that is being used here in this business to actually get at the end some numerical expression for C. But you can't, to my knowledge, do this analytically. It's still some sort of series expansions that you need to do. And this is a bit technical, but I just wanted to mention what's really behind it. Okay, let me conclude. So first message is, okay. So one thing I wanted to say, now a couple of slides ago, I mentioned earlier work by Ori and group and Diaz. So Diaz et al. Did this in the BTZ case, which is a kind of black hole with an inner horizon. And they found that this constant C was actually 0 always, which is kind of interesting. And so we redid their calculation with our methods and found the same result as we should. But you see that there is something very special here about the BTZ black hole, and in this kind of thing just does not happen in higher dimensions. So there is nothing wrong about their work, but it's just so seems that the BTZ black hole is not very informative here concerning this issue. And I should mention, and I think I have already mentioned the work, the pioneering work by Ori and his group, who have studied specific states which would correspond to analyzing very special solutions in the classical case, so maybe one or two. So we believe that our analysis really is important because it's really this whole question is about generic initial conditions, and that's not about special states which may do this or that. So in this sense, I think the original work of Ori et al. Did not really conclusively answer this question about strong cosmic censorship and quantum effects, although it did make important contributions without doubt.
Actually, sorry, am I understanding this correctly? That you're saying that for a certain range of parameters of BTZ, mass and
for all parameters of BTZ,
the inner horizon of the BTZ is classically stable. Is that what the statement is?
Is classically and quantum mechanically stable, both, because C, this constant C, this is what gives the very strong divergence, and that C is just 0 in BTC. And so you're left with this, but this is very, very regular. You can tune this to be like 25 times differentiable. So this does not at all cause the Cauchy horizon to turn into a singularity.
But there's still no violation of cosmic censorship, right?
Yeah, there is a violation of cosmic censorship in BTZ, and in quantum theory, in the other cases, in 4 dimensions, the quantum effects rescue strong censorship.
I see. So the problem is still open in 3 dimensions.
Yeah, so in 3 dimensions, you have a violation. In BTZ, I should say,
yeah.
not generically in 3 dimensions, just in BTZ, you have a violation of strong cosmic censorship at the classical level, as you would have in 4 dimensions too, as you can have in 4 dimensions too, but also at the quantum level, which you cannot have in 4 dimensions. Okay, so let me reiterate these conclusions. So you could say that quantum effects rescue determinism inside 4-dimensional black holes, but not the BTZ black hole, which is anyways just a toy model. And the quantum effects are much bigger than the classical effect. So the quantum contributions to the stress tensor is much bigger than the classical contribution inside black holes, or more precisely near the Cauchy horizon. So that's certainly very unusual, because at the event horizon, quantum effects are much, much smaller, even though they give rise to Hawking radiation, but that's a teeny weeny little bit of radiation. Indeed, so outside the black holes, usually quantum effects are much smaller than any classical perturbation. So that is, I think, the take-home message. I think I'm going to stop here because I've already done half an hour before that. Okay.
Thank you so much, Stefan. Are there any questions for Stefan?
I wanted to ask a question.
Sure.
Can you speak up a little bit?
Yeah.
Can you hear me now?
Yeah, I can. Yeah.
So you stated that when C is greater than 0, the Anek is respected.
Correct.
Right? But wouldn't we have to find the expectation value of all null components of the stress tensor?
Sure, but yeah, that's correct. But it's the VV component that's the interesting one. And so it's the geodesics that fall into the cross the Cauchy horizon. The other ones, the stress tensor is not singular.
Okay, but can we say that the integral of TUU along the null geodesic would be positive as well?
No, you can't say that in curved space, but it would be a finite number. The difference is that it's not only violated, but it's sort of infinitely violated. So in curved space, you do not have a statement that TKK integral is greater than or equal to 0 in all states.
But isn't
That's totally irrespective of black holes or anything.
But isn't the statement of the Anek that all null geodesics of all null components of the stress tensor should integrate to a positive quantity?
That's correct.
So,
and in curved space, that's just not true if you don't include somehow back reaction.
Okay.
Yeah, I mean, I think Anek is still a fundamental. Well, maybe my guess is that it's still a fundamental statement somehow, if you could make sense of quantum gravity properly, but you would have to include back reaction. But until really this TVV gets huge, the Planckian basically, the back reaction onto the metric is really small. So before this kind of turns around somehow, it's going to be very negative at first.
Are there any other questions?
So I'm not so sure about this, but is there a similar story when the cosmological constant is negative?
Yeah, on the BTZ, it's though a little. Yeah, the BTZ has as you probably know, has a negative cosmological constant. So it's a little subtle what you mean. Let's see. So you can still analyze this, and I believe there can be classically a violation of the strong SCC, strong cosmological censorship. But the explanation in terms of redshift and blue shift is not so evident as in the other case, because ADS is static, so there is no infinite redshift or something. There is no redshift effect.
I see. So it can be classically violated as well.
Sorry, can you say that again?
So it can be classically violated as well.
Yeah, I think so. I mean, in the BTZ case, definitely it is.
Okay.
I'm not so familiar with other ADS type black holes. All I'm saying is that it is not such an intuitive, at least not to me, maybe to people who have a better intuition about holography and things like that. To me, there is no such intuitive understanding why it's violated classically. But that doesn't mean much.
But the fact is, while even quantum mechanically, doesn't that pose a serious problem for ADS-CFT, or something to explain at least, right? ADS-3-CFT2?
Well, I mean, I think first of all, it's very good, because I think if the violation of strong cosmic censorship would be pretty disastrous, because it would really mean that you can't if you can't rescue it with quantum mechanics, then you have really a problem at the classical level. And so it's also very reassuring that it's saved by quantum effects. I think it's a very interesting self-consistency check of everything that's quite non-trivial. But
sorry, no, I didn't understand. So I thought your statement was that it's not saved by quantum, correct?
no, it's saved by quantum. So you want the Cauchy horizon to be a singularity.
Oh, I'm so sorry. Yeah. Sorry. Yes, correct.
Yeah,
correct.
that's what
Correct.
you want. That's what Penrose said. He said it's a singularity. So just
That's right.
this
Sorry,
Penrose
yes.
diagram that you draw for these space-times inside a black hole is an illusion. I mean, it's not. I mean, that's what you want. But I mean, this is what can be just not true classically. I mean, as these like in the BTZ case. I mean, the classical waves can be very, very regular at the Cauchy horizon. Yeah, but what this tells you about holography, I'm honestly not so sure, because yeah, I think there have been papers. You'd have to probe these inner horizons somehow holographically by some surfaces that go through the black hole, I suppose. But yeah, I don't know. It's an interesting. I have nothing to say really. There is a literature, but I mean, there is also let's see. I mean, I feel there's also maybe an information theoretic twist to it, because maybe I shouldn't say. Maybe that's too speculative. But there are perhaps some other ways of understanding it, as you point out. Maybe holography, maybe more general ideas that could explain, shed light on this, other than this very technical calculation in the end that shows that some quantity diverges.
Are there any last questions for Stefan? If not, let's thank you, Stefan, again.
All right, you're welcome.
And thank you so much for the talk.
Yeah, let's fix a time for our meeting.
Sure.
Yeah. All right. See you.